Our study today is on relations and functions, and we're also going to touch on linearity and function notation. First up, we have some vocab, starting with what is a relation. Well, a relation is basically a pairing of input values with output values. We will often see this written like x comma y. We know that x is the input and y is the output because we've seen stuff like this before. And this is really a driving force in mathematics in general. So we have this pairing of input values with output values. One way that we can represent this is with points like this. We will also represent this with equations like y equals m, x plus b. We have this equation where x is where you input the value and y, whatever you get out would be the output, the y. We're also going to see this in other forms, which we will get to in a minute. All of the possible input values of that specific relation would be the domain, and all of the possible output values would make up the range. So domain is associated with input, which is associated with x, or you might refer to it as the independent variable as well. Range would be all of the possible y values or output values, and that is the dependent variable. Now, a function is a special type of relation. So it is a specific pairing of input with output values where each input has exactly one output. This is one of the most important things that I want you to take away from this lesson is to be able to identify what is a function and what is not a function. And it's a difficult task. They're often conflated. But just to be able to say, yes, that is a function when I give you some sort of relation, or to be able to say, no, that is not a function. So how are we going to do that? We got to cover that. So going back to just what is a relation, and I talked about, hey, we can represent this like an ordered pair. Okay, I'm not asking for you to identify the pattern or anything. I'm just saying, hey, we can write relations as ordered pairs. We can write relations as tables, or as graphs, or in a mapping diagram. For each one of these, you're going to see the input is the x value. Here is the first number listed in an ordered pair, and the y value would be the second number. In a table, same thing. X's go on the left, y's go on the right. In a graph, the x's go left to right, and the y's go up and down. And then in a mapping diagram, the x's are on the left, and the y's, the outputs are on the right. I didn't ask this question right now, but if I did, say, hey, what is the domain? No, I actually back up. I want you to notice that this is the same relation represented in 4 different ways. It's always -2 is paired with 2. -2 is paired with 2. -2 is paired with 2, right? -2 is paired with 2. It's representing the same relation in 4 different ways. You guys should be able to go between any of these. If I gave you a mapping diagram, you should be able to give me a graph. Or if I gave you a table, you should be able to give me a mapping diagram, and vice versa. If I did ask for the domain, what I would be asking for you to do is list the x values that are represented in the relation, and I would ask for that to be in increasing order, in numerical order. So the inputs are -2, 0, and 3. We use set notation for this, which is these weird brackets, -2, 0, and 3. This is the domain. The domain is just asking what x values are ever in this relation. And if I ever ask for the range, similarly, those are the y values. We use the same notation, these weird brackets, and we list the y values in increasing order. The minimum y value is -2, and then it would be 1, and then it would be 2. That would be the range. So going back to what is a function, each input has exactly one output. I like to think of functions as a vending machine. I actually call the vending machine a function machine from time to time. That's kind of a weird math quirk. In a vending machine, you have inputs. For example, you go up to the vending machine, it's got the little buttons, and you type in C3. Because C3 gets you Gardettos, and everybody knows the best thing in a vending machine would be the Gardettos. So C3 would be your input, and Gardettos would be your output. If I wanted to write this as an ordered pair, I would write C3, comma, Gardettos. Input, output. In order to be a function, each input, C3, can only have one output, Gardettos. Okay? I should never walk up to a vending machine and type in C3, and sometimes it gives me Gardettos, which is the thing I want, and sometimes C3 gives me, I don't know, broccoli. Okay? If I input C3, I better know exactly what I'm getting. If I don't know exactly what I'm getting, that's a broken function machine. It's not actually a function, right? That would never happen in a vending machine. It's not like some lottery where you go in, you type in C3, and sometimes you get the thing that you want, and sometimes you get something that you absolutely don't want. Broccoli from a vending machine, right? That would be atrocious. So the point that I really want you to take away from this is when you type in C3, that's your input. You better know exactly what you're getting out. It better have a defined output in only one thing. C3 better get me Gardetto. Now, a dream vending machine, the perfect vending machine, has all Gardettos. Gardettos, 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 Gardettos. So whether you type in C3, you get Gardettos. You type in C5, you get Gardettos. No matter what you type in, C1, well, guess what? Gardettos. If that was the vending machine, and it was only Gardettos, and you typed in C1, you got Gardettos. You typed in C3, you still got Gardettos. That would be a working vending machine, would it not? Like, it seems weird, but the vending machine you would not say is broken. It's just only got Gardettos. It must be out in front of Mr. Necklace Room because that's all he wants anyway, right? So the difference is what's not a function would be if you typed in C3, sometimes got the thing you wanted, and sometimes you got something you did not want. It would, so that would not be a function. It would be a function, albeit a bit weird, if you typed in C1, you typed in anything, and no matter what you typed in, you got Gardettos. That would be an allowable vending machine. So let's look at this mathematically. Is this relation a function or is it not a function? The thing that perhaps would be weird about this one is we notice that -1 and 2 both go to the output of 2. So in this weird vending machine situation, okay, if you want to think of it as that, -1 gets you Gardettos and 2 gets you Gardettos. They got you the same thing. Is that okay? And the answer would be yes. Right? We can also go back to the definition if you don't like the Gardettos example. Each input can only have one output. Each input can only have one output. I might actually write that phrase in my notes. Each input can only have one output. Right here, this is fine. This is a function. Yes. What about this one here? This is the example, if we're thinking of it like Gardettos, you type in 1, sometimes you get nastiness, sometimes you get Gardettos, but you don't know which one. Okay, that would be broken. This is not a function. It's only a relation, not a specific type of relation, which is a function. Going back to the definition, the input of 1 has multiple outputs. That's what's not allowed. So that's covering it from like ordered pairs or a mapping diagram. If we are deciding if something is a function from a graph, it's actually a little bit easier. We have something called the vertical line test. And what the vertical line test states is that if I have a vertical line, that was an attempt at a vertical line, it's not, there we go. Okay, I've got a vertical line. If I can drag my vertical line across the entire graph, and it only intersects the graph in one spot at a time, it's a function. So let's look at some popular graphs. Let's look at just a line, okay? Is this a function or not? Well, if I drag my vertical line across the graph, it only intersects at one spot at a time, right? No matter where I put it. Therefore, it is a function. I can move this line weird ways. Still, when I drag this across, it only intersects in one place at a time. Therefore, it is a function. What about this U-shaped graph? When I drag my vertical line across the graph, it should only intersect at one place on the graph at a time, and it still does, right? Right here, it would be intersecting there. If I kept dragging it, the intersection will just become higher, but it still only intersects at one spot. However, if I took and rotated that, this would fail the vertical line test because there are places where when I draw my vertical line, it intersects in more than one spot at a time. Therefore, this sideways U-shaped graph is not a function. Function or not, I did draw this one already. When I draw my vertical line, it's not vertical, but pretend. All right, only intersects in one spot at a time. That one would intersect in more than one spot. Or like a circle, fails the vertical line test, right? When I draw a vertical line, there are places that it intersects in more than one spot at a time. All right, to graph equations. You guys don't know how to graph equations yet using your graphing calculators. The way to do that is, and I don't have access to a graphing calculator at this time, but the way to do that is going to be to push the top left corner button, which says y equals. And then you should just be able to type in 3x minus 5. The x button on your calculators looks like this: x, comma, t, comma, theta, comma, n. It's a button that has all that on it. So that'll give you y equals 3x minus 5. And then you're going to type in the top, you're going to push the top right button on the calculator, which says graph. And then it should graph it for you. I'm going to make a special video on that and upload it when I'm done with this. But we could also graph this kind of the old-fashioned way if we needed to, if we didn't have access to a graphing calculator at the time. We could either do -2, -1, 0, 1, and 2 in for x and see what you get out for y. Or if we remember slope-intercept form, -5 is the place that you start on the graph. And then you could rise 3 and run 1 from there. 1, 2, 3, run 1. 1, 2, 3, run 1. So that would be, that's kind of a quick review of graphing. We'll spend more time with that later as well. One thing that's incorporated in this section is called function notation. And you guys are really used to using y equals mx plus b, or like y and x as your independent and dependent variables. As you proceed in math, you're going to see y equals less and less often, and instead you're going to see f of x equals. F of x is equal to mx plus b. I want to point out right away that although it does look more complicated, it doesn't have to be. You can always remember that f of x means y. One reason that we like f of x more than y equals is that it tells us right away that it's a function. This is function notation after all. If it uses f of x, we know it's automatically a function. But that isn't exactly why we like function notation, and I'll show you why here on this next slide. So currently we have f of x equals x plus 5. We know that f of x is the same as y equals x plus 5, right? However, like I said, we're going to start using f of x instead of y. What does that allow us to do? Well, notice that there is not an x there, there's an 8 there currently. This is my equation, and f of 8 is actually a question. What f of 8 is asking you to do is it is saying, what do you get when you plug 8 in for x? Because x is supposed to be there, but it doesn't have x there, it has 8 there. So what it's asking you to do is tell me, what do I get when I plug 8 in for x? So not only would you plug in 8 in for this x, but you'd also plug in 8 for this x. Over here, we'd have f of 8 is equal to 8 plus 5. I want to point out and highlight that this does not mean f times 8. Students often think that that's what it means because that's what parentheses historically has meant for us. It doesn't mean that. Okay? When you see f of 8 or f parentheses 8, that means f of 8. All that's saying is we took 8 and we plugged it in to our equation. It cannot be simplified. It's just going to say as f of 8 is equal to 13. So this looks weird to us, this right here, but that's our answer. And you are going to get better at reading this. What this is telling us right now is that we took 8 and we plugged it in to our equation, and what we got out was 13. We plugged 8 into the function, and we got 13 out. Now, set this aside for a minute. I'll come back to it. If I were to ask this the old-fashioned way, right, with y equals, I would say the question that I would have to ask is, what is the value of y when x equals 8? And then you would plug in 8 and you would say y equals 13. Now, this is not a true statement. Y isn't 13. Y is only 13 when x is 8. So I would actually have to write y equals 13 when x equals 8. And that's a lot of writing. And mathematicians are historically pretty lazy people. And so we've developed this notation that allows us to say all of these words with just symbols. And that's really what we want to be able to do. So instead of saying, what is the value of y when x is 8, and then plugging in 8, what we can do is we can say, hey, what is f of 8? And what you would do is you would plug 8 in for x, and then to answer it, you could just say, hey, f of 8 is 13. I plugged 8 into f, and what I got out was 13. Let's erase this. Let's try this whole part again. So we got another one. So this one's G. It doesn't matter what letter you use. Historically, we use f because it's function. But we don't want to say, hey, f of x is this, and f of x is something else on this side. Okay? Because f of x, we're saying, is a specific function. We're calling it f, and it's x plus 5. Over here, we're going to define a new function. So we're going to call that function g this time. We don't want to say f of x and then define f of x to be something else over here. We want to use new letters. And so most often, what mathematicians will do is they'll define the first function as f, and the next one is g, and then they proceed in that fashion. So function g is x squared minus 4x plus 1. What is g of 3? Remember, what you do is you plug 3 in for anywhere where there's an x. So you'd say g of 3 is equal to. Now, I talked to you guys about when you substitute something in, put it in parentheses. Do not simplify g of 3. G of 3 is completely simplified. It's saying, hey, you plugged 3 into g. What did you get out? G of 3 is equal to 3 squared is 9, minus 4 times 3 is 12. Negative 3 plus 1 is negative 2. Remember what this is stating. I plugged 3 in for g, in for x in g. Okay, I plugged 3 into the equation, and what I got out was negative 2. I believe this is the last topic of this section, is is the function linear? On the tests, a lot of people mix up, is it linear and is it a function? Remember, is it a function is asking, is there only one output for each input, right? Each input can only have one output. Is it linear is asking, when I graph it, does it make a line? Or does it make a U or a V or, a step or different things, okay? When I graph it, does it make a line? And so here's things that you should know that do make a line. If it can look like y equals mx plus b, this is the traditional way to write equations of lines. Y equals mx plus b. Here's some things that are not linear. If it has an x squared in it, or a y squared, or a square root of x, or a square root of y. If it has x times y, or if it's like 1 over x, where x is in the denominator, or if it has absolute value of x, or absolute value of y. Okay, none of these things that I just listed look like y equals mx plus b, right? Y equals mx plus b is very basic, traditional. There's a y and an x, and they're separate. Any of these things would be things that are not linear. I could add like x cubed or y cubed, where it's got a different exponent than squared. But those are the really common things that you would see that would be not linear. Also, if like x was up in the exponent, it was like 3 to the x, that would be not linear as well. So here you have a function f. Remember, this does not mean f times x. This is just saying a function. You could imagine f of x to be y. Is this linear or not? Of course, this is not linear because it's got that x cubed in it. This one here would be a function. Okay. Not only you could think of it as not having any of that stuff, right? G of x is the same as y, so it would be like y equals -4 minus 2x. That looks a lot like y equals mx plus b. In fact, I could convert it into that if I wanted to. And there's no exponents, there's no square roots, no absolute value signs, none of that weird stuff. So that one there is not linear. Sorry, that one is linear. This one is not linear. That's all I have for you guys today. Let me know if you have any questions.